your quality control charts and you know that your process is in control, then we start to see whether this process now is capable of meeting the market requirements on your individual product. So I share now the PowerPoint. Okay, we want to talk about process capability analysis. And as I said, you start process capability analysis when you finish your quality control charting. Devi has already mentioned to you that when you're using the quality control chart like XBAR or R chart or P chart, if you have a point falling outside your control limits, you have to first find the reason for those samples being out of control. If you could find those reasons, and it is very important, if you could get rid of those reasons, for example, you had out of control product because the raw material that you were using wasn't good. So you are not going to use that raw material anymore. In that case, you find the reason for your out of control and you can get rid of it. So you remove the points that are out of control and you look at your chart again. If everything is in control, then we say the process is in the state of statistical control, or sometimes we say the process is now stable. For a stable process, then we are allowed to look at the capability of that process. Every product that you're producing, the market give you some specifications for it. For example, if you are buying a computer, in your contract, the Apple says the battery life for this computer is between 6 hours to 8 hours in the first 2 years of your computer. So the 6 hours and 8 hours are the specification limits on the life of your battery. Now, the interesting thing is, unlike the quality control chart, when you used to take a sample and calculate the mean or range or standard deviation and see whether your process is in control or not, when it comes to specification limits, the limit that the market give you must be applied to every individual product. So here we are talking about each individual product, not the mean of your sample, not the range of your sample. Because as a customer, if you buy a computer, you expect the life of your battery to be between 6 to 8 years. So you individual, your own individual computer need to meet those specification limits. Specification limits in the market, depending on what product you are using, sometimes is called specification limits, sometimes is called tolerance limit, and sometimes is just called conformance limit. So you use different things. I highlighted the word individual unit here because I want you to remember that is applied to each individual product. Sometimes your product or what you are monitoring has got two-sided specification limits. The example is like the life of your computer battery. It has got, say, between 6 to 8 hours. So that is two-sided specification limit. The upper specification limit is usually presented by USL, upper specification limit, and the lower specification limit is LSL. But sometimes you are monitoring products that doesn't have two specification limits. A very good example of it is if you are monitoring the pollution level in your city or in the water. For the pollution level, we don't care how low it is. So there is no lower specification limit for it. But say in Australia, we have ozone reading, which we try to monitor it, especially during the summer month. And for that, we only have upper specification limit. And we say if the level of ozone is above 7 in reading, then nobody is allowed to work outside. So there are cases that you only have upper specification limit and it matters to you. Even the life of your battery, the upper specification limit doesn't matter to us. You don't want it to be less than 6 hours in the first 2 years of its life. So depend on what you're monitoring. You can have two-sided specification limit or only one-sided specification limit. Now, if you are a manager and you're producing something like Apple Company, as a manager, your task is to make sure every individual product meet this specification limit of battery life between 6 to 8 hours. So even if your process using control chart is in control, because in there you are looking at a mean of your sample or range of your sample, it doesn't mean that your process is also capable. So that there are cases that your process is in control, but the product that you are producing do not meet their specification limits, and therefore, example like Apple Company, each person who buy a computer and the lifetime of the battery is less than 6 hours, you can return it to the company and ask for your money back. And that is very expensive for the company. That is why we try to make sure before we send our product to the market, the product meet specification limits. Okay, the next question is, how do we measure this specification limit? We cannot check every individual product before we send it to the marketplace, because that is costly. In the example of the computer lifetime, when you want to check the capability of this product, you take one of these computers randomly and you run it 24 hours and you check within a week or 2 weeks whether the life of your battery is really between 6 to 8. So in fact, you destroy one of your computer every time that you want to test whether it is capable or not. And as a manufacturer, you cannot do that. So how do we measure it? There is an index called capability ratio index, and there are 3 ways that industry present it. They can just use the notation PC. In the engineering area, they usually use the notation C index P, or sometimes just process capability ratio. Minitab usually uses this one because Minitab is designed mainly for engineers, and so it uses the notation that is familiar for the engineers. How do we calculate this capability index? The market on every product, or when you are manufacturing something, before you write your guarantee, like Apple company's guarantee or your mobile guarantee, you have to say what is the upper specification limit and what is your lower specification limit. So your PCR is the difference of these two divided by 6 sigma. That is, when you collect the lifetime of a lot of Apple products and you find its variability. So that is sigma on the lifetime, not the mean, not the range, just the standard deviation of the lifetime of your battery. Now, if we want to write this in word, upper specification limit minus lower specification limit, in fact, is the allowable spread that the market has allowed you to have on your product. And you have already studied quality control and you know a statistic. You know that if your data follow a normal distribution, 99.7% of your data fall between mu plus minus 3 sigma. So in a statistic, we always call that 6 sigma the natural spread of your data. And please pay attention, what I'm going to what I'm discussing today, this is your based on normal distribution. So I'm assuming here the quality characteristics follow a normal distribution. So when you calculate your PCR, what is the expected value that you can have for it to say this process is capable? They can say 1, but I discussed that 1 later on. The magic number for your limit of process capability ratio is 1.33. That is if your process has been in place for some times. But if you have got a new process, then we increase that value to 1.5. And I tell you why. If I go back to the previous page and the formula for your PCR, you can see on the top, you have got the difference between your lower and upper specification limit. And in the denominator, in the bottom, you have got sigma. So the only way that you can increase the value of your process capability and larger process capability is better. The only way that you can increase it is either to have a larger specification limit, which is not always possible. For example, in the Apple computer, they can tell you your lifetime for the battery could be anything between 6 to 12 hours. So they give you a large specification limit, or you can reduce the variability in your process. Usually, the reason that we say for a new process, we want a larger PCR, often the aim is to make sure from the start of your production line, you have a small variability between the quality characteristic that you are measuring, because a smaller variability means the product that you are producing are uniform. So every time that we talk about increasing your PCR, often what we want is to reduce your sigma. However, there are quality characteristics that you want to have a large specification for it. For example, if you are using concrete, that you want to build a road, you want the strength of this concrete to be wide, because if it is very cold, you need to have a smaller tolerance. And when it is very, very hot, you still want your concrete strengths to be there. So, or if you are building a bridge and you are using these metal bullets to keep your bridge safe under the knees, you do need a large specification limit, because sometimes you have got so many traffic on the bridge, so these bullets should be able to hold their strength. And sometimes you have very few cars on the road, so you need the bridge to stand without any crack when the load on the bridge is low. So there are circumstances that is okay to have a large specification limit, but often our aim is to reduce this sigma. Now, in your formula, because you have got sigma involved, upper and lower specification limit always must be designed before you start producing something. Sigma, sometimes you don't know the real variability of your measurements. If that is the case, then collect a lot of measurements on your quality characteristics and calculate the S or R to estimate the standard deviation of your process. Now, as I mentioned earlier, if your quality characteristics relate to the safety, strengths, or performance features, such as bullets that you are using in the bridge construction, then you want it 1.5 for the existing process, and again 1.67 for the new process, for the same reason that I said. If you are producing these bullets, you have to make sure that it can take very light load and very heavy load. So you want your upper and lower specification limit to be further away from each other. Now, if you are in a situation like the pollution or the lifetime of your battery, as I said, all of us are really worried about the lower specification limit. We don't want our new computer has a battery life less than 6 hours, so we only concern with the lower specification limit. If you have only one specification limit on your product, you can still calculate your process capability index, but its minimum and maximum accepted value would be different, and I'll go through it in another table. So if you only have upper specification limit, then that is how you calculate your PCR. It is upper specification limit minus mu divided by 3 sigma instead of 6 sigma, and your lower one is mu minus your lower specification limit divided by 3 sigma. Now, before I go to the next section, I want you to pay attention here. If I go back to the previous page, you see when you are calculating your process capability index for a two-sided one, the mean of your process is not involved in your formula at all. So your process capability ratio doesn't take into account the mean of your process. It only takes into account sigma. And that is a problem as we go through it later on in the example. But when I go to the one-sided specification limit, you see the mean of your process is also involved. So having this one allow you to have some judgment on the mean of your data as well. Now, whether you're calculating a two-sided or one-sided process capability, if mu is unknown or if sigma is unknown, you can use a lot of historical data that you have collected, estimate the mean X bar, and estimate the sigma S, and use it in this formula. And if you do that, then we use the hat on it to say this is not the actual capability, it's the estimate of your capability. I thought I'd go through one example, and forgive me because we are all working from home. So I didn't have access to photocopy machine and so on. I had to write it by hand and submit it because I didn't have document camera at home. So let's look at one example. Here we have got some data that are obtained on machine cylinder bores in an engaging in an engine block. You know that when you're drilling a hole, the direction that you have got and you're drilling this hole matters. If you change your hand angle, the hole diameter changes. So this data is collected when the angle of press is kept at the same place. So you have collected a sample of size 5, and your measurements on the diameter of the hole is supposed to be 3.502, 3.506, and so on. And Debbie probably has talked to you by now. Because this diameter is very sensitive, the first 2 digits doesn't change. The only thing that changes is the last 3 digits. So the data are decoded here, and only the last 3 digits are given. So you want it every time that they ask you to assess whether this process is capable or not, even if they haven't told you, do the quality control. You first must do the quality control chart to make sure that everything is in control. So here it says use X bar and R chart to see if your process is in control or not, and then find the percentage of the product that fall outside the specification limit of 203 and 1.95. Then, is this process capable of producing product within the specification limit? The only way that you can answer this question is calculate your PCR and compare it with the value of 1.33. If it is more than 1.33, you say is capable, otherwise you say is not capable. Then it's asking you to center your process. So forget about the actual mean of your process. Use the nominal mean. The nominal mean in quality control is very important. Your production line is doing very well if the mean of your measurements is equal to its nominal mean. The nominal mean is at the middle of your upper specification limit and lower specification limit. So its value is upper specification limit plus lower specification limit divided by 2. So in this section, it says, forget what is the mean of your process. And here, the mean is not given and sigma is not given. I only have some data. So I have to calculate the mean of my data, X bar, a standard deviation of my data, and use it as an estimate. But in this part, it says, forget about the mean that you have got based on your data. We want you to use the nominal mean and tell us what percent of the product now falls within your specification limit, and is asking you whether this has changed or not. Are we okay for me to continue, or do you have any question that you want me to answer?
Ada yang mau ditanyakan dulu atau lanjut? Ada yang mau bertanya atau dilanjutkan?
Dilanjutkan.
Dilanjutkan. Okay. Mali, you can continue first.
Good. Okay. So they don't have a problem with the English?
No, Mali, I think they can understand well because you speak English very slow and then can clearly understanding.
Okay. So we go through first. What I'm going to do is I give you the Minitab output for this process, and then I go through the hand calculation. Okay. Uh, okay. So this is your data. I'm sorry, there was a lot of data, and I couldn't make it larger than that. But you can see that each row presents one of your sample. You had a sample of size 5. So on day 1, these are your last 3 digits for your the diameter of the hole that is produced, and so on. So that is your data, and all together you have got 35 data, the 35 samples of size 5. When you are using Minitab, you have got 2 ways to analyze your process capability for the data. First of all, when you are using Minitab for process capability analysis, you have to have all of your raw data. You cannot have only the mean of the sample or a standard deviation of your sample like you used to have in the quality control case. The reason is when you are using quality control chart, all you are plotting in your chart is just the mean of your sample or range of your sample. And it's that. So you don't need your actual data or reading for each sample. But in the process capability, because we are looking at each individual measurement, you have to have the actual reading for each sample. And as I show you later on using Minitab, we use all of these what we call raw data. So I have used all of my raw data. The only problem here is, first, when I used all of my data in the XBAR and R chart, I had these following 4 samples falling out of control. So I had sample 1, sample 6, sample 11, and sample 16 being out of control. So I assume the reason for this data to be out of control is known, and we could get rid of those reasons. So I removed these 4 samples from my data, and I'm using only 31 samples here out of the 35 original samples to do the capability analysis. This first graph shows you the full capability analysis in the Minitab. And by the way, even though you can use R or Excel to do your quality control assessment, Minitab is one of the best packages to carry out your quality control assessment. Minitab is a very popular package in America for engineers when they do quality control. So they continuously update this package based on the feedback that engineers give them. So if engineers say, I want more information on the performance, on the capability analysis, then the team of Minitab goes and develop the next version, which is more complete, and so on. So when I teach quality control, I usually use Minitab. And that is one of the best graphs that you can see really to look at the capability of your process. Okay, let's see what this package has got. it has, when you are using it, you have to enter your upper and lower specification limit. That is a must. Otherwise, you cannot run the statistical package for capability analysis. The mean of your process either is known, so you can put it, or is not known. The statistical package calculate the mean and standard deviation using your data, just like it used to do for the control chart. In your graph, so you can see I've got the upper and lower specification limit put in there. I didn't have the mean or a standard deviation, so a statistical package is doing it. And when so you had got 155 data all together here on this graph. And because I didn't have a standard deviation, Minitab has calculated the standard deviation and is giving you two standard deviation, within and overall. If you want to use the within standard deviation, is a better estimate, because overall it uses sort of the distribution that is fitted to the data and give you that value. So if later on you want to use calculation, use always the standard deviation within your data. Then on the right hand side of your graph, you have got the value of CP, your process capability. And you can see your process capability is 0.45. And we said your process is capable if the process capability index is above 1.33. So definitely, based on your CP, you can say this process is not capable of producing most of our product within the two specification limit. Now look at the graph. These are your histogram of your individual measurements, and the statistical package is trying to fit two normal curve to it. The black one is in fact based on all of your data, and the red one is it simulate more data and it tries to fit the data. So you can see your data is normal. So we don't have a problem with that. But look at your upper specification, lower specification limit, and upper specification limit. You can see you have got a lot. These are your actual data. So you can see a lot of data are above your upper specification limit, and there are data below your lower specification limit. So definitely this process is producing a lot of waste product because they don't meet the specification. Then we go through this nice information at the bottom of your screen. Here, it tells you the number of data per million for this process that is smaller than your lower specification limit, or is larger than your lower, or is above your upper specification limit. And then when you add both of them, that is the total data that you will have for this process out of a million to be outside your specification limit. So out of million, you will have 154,838 products falling outside the specification limit. That means if you start making a shipment of million from these products to other companies, you may get this many products coming back to you and you have to replace it. And that is a huge, huge loss to your production line. So that is a very bad process. This is observed out of million based on your actual data. Then you have got expected performance within your data. That is when is using this black curve and is estimating in terms of probability how many you will have outside. And you can see that if you try to feed a distribution, then the number outside your specification limit per million is even higher than your actual data, because that is based on 155 data only, calculating the probability and based on the mean standard deviation and multiplying by or looking at it per million, but that is using the gap. And then this one is using simulation and that red curve and estimating the proportion falling outside, which is something between these two. So this process in general is not a good one, and that is the whole story that you can present. The rest of this, I haven't discussed that. You already seen a one-sided process capability index, which is this and that. And I tell you what they are in it. So you have seen these two. You can see the upper specification limit is higher. The upper one-sided capability is higher than lower. And I tell you what this one is in a minute. Now, in Minitab, you also have the option of six-pack capability analysis. This option is good because it automatically checks the X bar and R chart for your data, and it also gives you some information on your process capability on the right hand side. But you see, I don't have as much information that I had in the previous graph. I do have my CP, which is 0.45. So it does still allow you to say whether this process is capable or not, but it doesn't give you the percentage per million and so on. So if you don't, if you haven't done the quality control part first, always the option of six-pack is a good option. Again, here I did run first the six-pack on all the 35 samples that I have, and I removed my out of control samples 1, 6, 11, and 16. So this is only based on 31 samples, and you can see the last point here plotted is 35. And you remember I said sometimes your process is in control, but is producing waste in terms of process capability analysis. In this graph, if you just wanted to rely on whether your process is in control or not, X bar is in control, R is in control. So you can say it's a perfect process. But when you look at your capability analysis, you can see its value is very small. But looking at the graph, you can see you don't have now a view of your upper specification limit, lower specification limit. So you don't see as much as you used to see in this graph. So use your six-pack if you haven't done quality control. But after that, attach your full capability analysis as well. Okay, in this graph, it shows you your data is almost normal, so you need to know that. It gives you the normal probability plot of your data as well. Now, remember I said the formula that I'm using today is based on the assumption that your quality characteristic measurements follow a normal distribution. So you have to check the normality of your data before you start analysis. When you are using the six-pack, it does give you the normal probability plot. And from statistic, you know that this is the 95% confidence interval for your normal line. And in general, if your p-value is less than 0.05, it says that your data follow a normal distribution. And you can see here my p-value is very small, so I'm sure that my data follow a normal distribution. Okay, now I want to do some calculation by hand. Here, what you had in this data, you only had the reading for 5 samples. So you need to calculate X bar and R for each individual sample. I have removed these 6 samples. So calculating my R bar based on 31 samples only, I've got 6.6. Your sample size is 5. So earlier, probably Devi has gone through the formula that if you only have the range of your samples and your sample size, in Montgomery, you have got a formula that you can use to calculate your control limits. And that is the formula A2 index is given in a table in Montgomery textbook based on your sample size. So I have used this value to calculate the upper control limit for X bar, which is 1995, which is 203, and the lower control limit for X bar, and the same for your R is 0 and 1. So based on these control limits, if you look at the Xi and Ri for all the 31 samples, you can see they fall within the control limits. So you can start saying that your process is stable. And then you want to calculate your capability index by hand and see if that is greater than 1.33. So for your capability index, you need the value of sigma, and I'm using cat because I'm estimating it. So that is estimate for sigma. Again, one of the formula in Montgomery tells you that is R bar over Bn. Bn is the index that is giving you based on sample size, and so that is estimate of sigma. So I can now say my individual product, the individual diameter, follows a normal distribution. The mean is the mean of all of your samples. Probably Devi has talked about it. If you are using the mean of all the mean of your samples, we use the notation X double bar. And in some statistical quality control, they call it grand mean. So that is, you calculate the mean of each sample, and then you calculate the mean of your means, and we call it grand mean. And that is your information. You already given upper and lower specification limit. So you want to know, the question is asking you, what percentage of your data fall within your specification limit? The percentage of individual diameter falling within your falling outside your specification limit is in fact probability of X being above your upper specification limit plus probability of X being lower than your lower specification limit. To calculate it, you standardize the normal because you assume your individual follow a normal distribution. So you subtract the mean divided by sigma, and that gives you probability of Z being, it gives you the probability of Z being greater than that, which is 0.1415. So that means in general, 14.14% of your data is falling above your or outside your upper specification limit. To calculate the percentage below your lower specification limit, you follow the same, and you can see 4% of your data fall below your lower specification limit, and therefore to calculate the total falling outside your specification limit is 18.2%. 18 to almost 2% of whatever you are producing is not accepted in the market and may be returned to your production line. That is very high. In general, if you go through the quality assurance, in there you learn that the maximum accepted percentage to be outside your specification limit is really 5%. That is the maximum accepted. So 18% is just too much. This industry is really bad. It will be costing you a lot to repair it. So you're calculating your PCR by hand. You can see its value is 4692. That, as I said, is less than 1.33, and your process is not capable. In the next part of the question is asking you to center the process at the nominal mean. So previously what I did was I calculated the grand mean, and you can see your grand mean here is 199.95. That is based on your actual data. In the second part, it says forget that and center your process when you're adjusting it as at nominal mean, which is upper specification plus lower divided by 2, and calculating it, it gives you 199. I'm using still the same standard deviation. And so now I want to calculate the percentage above your upper specification limit and percentage below your lower specification limit. The difference now is when I'm standardizing my normal, instead of 1995 that I was using, this is the mean that I use. And you can see the percentage is changing now. You have 7% above your upper specification limit and 7% below your lower specification limit. So your total falling outside now is 15.8%, which means when I centered the process at its nominal mean, I could reduce the proportion of defect or unwanted product from 18.2 to 15.8. In numerical number, you would say, okay, that is only 3%. But if you are looking at a million product, 3% is 30,000 product, which is huge. Okay. So when you start working in this area, if you are asked, how can I reduce the percentage of the product falling outside the specification limit? One way is try to center the mean equivalent to the nominal mean. That is always reducing the percentage of your product falling outside the specification limit. Now that we know the PCR, okay, one application of it was it has to be greater than 1.33. So we can say majority of our products is meeting the specification limit. But there are other interpretations for it. You see, in industry, usually we calculate P equal 1 over PCR multiplied by 100. That tells us the percentage of your specification limits that is covered by your products. If your PCR, if your product is capable, then your PCR is greater than 1. And that means this percentage is something less than 1. For example, it could be 1 point, your PCR could be 0.6. So your percentage would be 0.6 times 100. That gives you 60%. That means only the products that you're producing fall well inside your specification limit and only cover 60% of your specification limit, which is good. But if my PCR, like this example, is 0.5, then 1.1 divided by 0.5 is 2.2. Multiplied by P is 200%. And that means my specification limit, 100% of my product is falling outside my specification limit. So this percentage, sometimes when people want to buy your product, they ask you for the percentage of specification limits that is covered by your products, and they want this number to be less than 100%. That is the good thing about it. The other interpretation that we have for PCR, and is very important, is this, the second point. We said your PCR has to be 1.33 or greater than. The reason is, if my PCR is 1.33 or greater than, so using this formula, that means 1.33 is equal upper specification limit minus lower divided by 6 sigma. If I multiply 1.33 by 6, the answer is 7.9 something. So I can say that the upper and lower specification limit, the difference between them has to be greater than equal 8 sigma. That has got two applications, this formula. The first one is, let's say you have just started to use quality control in a production line, and you say, okay, you have done some, say in the battery life of your computer, you don't know really what should you put it as the upper and lower specification limit. So what you do is you produce some computer, you select, say, 200 of them, and calculate the variability sigma between the life of these batteries for 200 computers. So you have got your sigma, and then you sit with your manager and you say, look, based on what we have produced, I can see that my sigma is 1. The difference or the variability between the life of these batteries is 1. So what we can do is we look at the minimum and maximum, and we say the difference between our upper specification and lower specification limit has to be greater than 8 times 1. So you can see, put your lower specification limit just looking at your data and see what was the minimum number of hours that your battery was lasting. And then you say, okay, I'll put it, say, between 6 hours plus 8 times 1, which is your sigma. So you put it between 6 and 14 hours as your specification limit. And believe me, in a lot of industry, when you ask them what is the upper and lower specification limit that you want to put for process capability, they tell you, I have no idea. If that is the case, this formula is really good, tells you a limit for it. There is another application for it, and that is from both producer of the product and the customer who want to buy your product. You see, if I use this formula and calculate a limit for my sigma, so let's say I know my upper and lower specification limit, but I want to know how much I can reduce the variability in my product. So if I use this formula, I can say my sigma has to be 1/8 of your upper specification limit minus lower specification limit. Okay? So that is the second application of it, and that is very good. If you are setting up a new product, you already know from your customer your upper and lower specification limit. Say in the computer example, Apple has got the feedback from the market, and they know that for the customer to be happy with the laptop, the battery has to last between 6 to 10 hours. So they give you the upper and lower specification limit, and you take that into your factory workshop, and you say, okay, look, when you are producing this product, the batteries have to be designed in such a way that the variability between the lifetime of your battery cannot be more than this much. So you have got your limit for the sigma to monitor your process. Now, earlier, when I was going through the limit for your specification for your PCR, I said for the new product or for your safety measurements, you usually have a higher PCR. The higher PCR is either you have got larger specification limits or you have got a smaller sigma. In general, if you're helping a production line to design their specification limits, tell them that if the market allow you to have a large specification limit, go for it. Always large specification limit is much better than having a large standard deviation to increase your PCR. If my PCR is equal to 1, and some industry are happy with 1, what it means is, in this formula, that is equal to 1. And that means your upper and lower specification limit are in fact equal your mu plus minus 3 sigma, that we call it a natural spread of your data. However, if your PCR is less than 1, you have two circumstances. Either the difference between your lower and upper specification limit is very narrow. Sometimes that is the case. Say in the medical area, if a patient had just heart surgery and is in the ICU unit, blood pressure is very, very important. And because the patient is in the critical condition, the upper and lower specification limit for the blood pressure that the doctor gives you is very small. If that is the case, to improve the capability of the condition of your patient, the doctor has to make sure that the variability between the blood pressure is very, very small. So they monitor the blood pressure very, very carefully through the medication to make sure it doesn't go up and down from minute to minute or in the first 4 hours. So sometimes your PCR is small, and the reason is either this is very narrow. In that case, you talk to the market to see if you can improve that one, or often actually means your sigma is very high, which is not good. That means your products are not uniform and you try to reduce it. And if that happens, we usually call it type 1 conflict. You can look at when you get to the quality assurance, we talk about type 1 and type 2 conflict a little bit more. If you want to know about it, read the book by the reference book that Devi has put in your Montgomery PowerPoint. Now, this is a very important note. If you are asked to assess the capability, process capability, you have to make sure that your specification limits are valid. Because whether you have a one-sided process capability index or two-sided process capability index, your value is heavily based on your upper and lower specification limits. So if they are not valid, your process capability analysis is not valid. Devi, is there any question or should I continue?
Oke, Mali, thank you. Apa ada pertanyaan sampai di sini?
Bu Dewi,
Iya,
bisa
Bu.
yang bagian terakhir bisa diminta diulang. Saya tadi sempat tertinggal sedikit.
Yang berapa slide sebelum ini, Bu?
Persis sebelum ini. Okay. Yang validitas dari limit.
Oh, oke. Iya, Bu. Mali, can you please go back one slide from here? Ya. Ini ya, Bu?
Iya. Thank you, Mali.
What is the question?
I want to say.
Good, go on.
Can you repeat the explanation of this note, Mali? Thank you.
Yes. Let me go back to your formula. Okay, you see, if you want to calculate your PCR, in your formula you have upper and lower specification limit. If I go back to your one-sided PCR, you also have, you see, even in your one-sided PCR, if you only have only upper specification limit or lower specification limit, when you are calculating your process capability index, in your formula, you have upper specification limit and lower specification limit. So what I was saying in that note is this. That's when you want to say whether your process is capable or not, because you are using your specification limits, you have to first make sure the value that you have got for your upper specification limit or for your lower specification limit are real value. These are the correct value. And usually the value of your upper specification limit and lower specification limit are given to you by your customer. So if I'm going back to the example of Apple company and looking at the lifetime of the battery, I cannot just make my own judgment and say, okay, if the life of the battery is minimum 2 hours, the customers are happy. This is not a valid specification limit. I have to go to the market and listen to the customer, and if they tell me the specification limit has to be between 6 and 8 hours, then that is a valid specification limit. So that is what I'm saying. And as I said, unfortunately, a lot of the time, when you go to quality, to the industry, and you want to assess the capability of their process, you ask them, what is your upper and lower specification limit? They say, I don't know it, or they say, well, let's assume this. That is not a good example. They have to have a valid value. In the next few slides, I tell you that if they really don't have any idea on what is the specification limits, how can you design a natural specification limit to start with, and then send this product to the market and see the feedback of your customer, and then build a better specification limit? Is that clear now?
Okay, thank you, Mali. It's really clear. So
Okay.
we need to use the information before we make a PCR. Right?
Yeah.
Okay, thank you, Mali.
Okay. Okay.
From students, any more questions? Or otherwise, we can continue, Mali.
Okay. All right. The next thing that I want to talk about is the confidence interval for the PCR. Let's just go back to what we were teaching you in the statistic, just in a statistic. You remember in the statistic, we said if you want to estimate, for example, the mean of your data, you can just calculate X bar and say this is an estimate for the mean of your process. Then later on in a statistic, when we teach you confidence interval, we tell you the mean is an estimate. The X bar is an estimate for your mu. But every time that you change your sample, you get a new value for X bar. And so is not a very reliable estimate for your mu. That is why instead of X bar, we use a confidence interval for estimating your mu, and we say, okay, based on this sample that I had, the mean of my process is falling between, say, 6 and 12. So the concept of confidence interval is always important, because instead of giving one value as an estimate, allow you to give a range for your estimate, and is more reliable, and industry can count on a range rather than the things. It's the same story for your PCR. Instead of me saying that I selected these data from your production line and I calculated the sigma for it, and I came up with the value of, say, 1.45 for your PCR, just one value. I know that if I change my data, the estimate of your standard deviation changes because your data is changing, and therefore you get a different value for your PCR. So instead of giving just one estimate for your PCR, you can use a confidence interval for your PCR. Now, because your PCR, in your PCR, upper specification limit and lower specification limit are two numerical values, okay? The only thing that is obtained based on your sample is the estimate of your sigma. So when you want to estimate a confidence interval for whole of these value, the distribution that you fit to it is the distribution that you can fit to sigma. In your basic statistic, I don't know whether you have been taught that or not, but in general, when sigma is involved and you want to fit a distribution to it, there are two distributions that fit to sigma. One is chi-square, the other one is F distribution. Often chi-square fit sigma as a distribution better. So to estimate your PCR, 95% confidence for PCR, we use the chi-square distribution, and the formula is that. So you estimate your PCR just like in basic statistic. You used to estimate X bar based on your sample, and your 95% confidence interval was X bar plus minus 1.96 sigma over the square root of n. Here you estimate your PCR using estimate of that. So you have this value, and then you use the chi-square to define the 95% confidence interval. And you see, this looks much better. So if the industry who want to buy your Apple computers come to you and say, okay, what is your capability index? You don't say is 1.5. You say, look, my capability index fall between 1.25 and 1.65. And these products are good because both the lower specification limit and your the lower confidence limit and your upper confidence in limit both are above 1.2 or 1.3, and so that the person who want to buy your product have a better idea in the range of the capability index that you have got. Any question?
Ada pertanyaan lagi? Maybe you can just continue, Mali.
Okay. Okay, now I move to the next section. You see the process capability ratio as we defined it here. It takes into account only the standard deviation of our data. It doesn't care what is happening to the mean of your data. But you have already studied quality control chart, and you know in the quality control chart, the mean is very important. So after 10 years that the industry was using the process capability index, they came up and they said, hey, look, now we need a new capability index that take into account not only the standard deviation, but also the mean of our process. Because we want to know if the mean of our process is getting away from the nominal mean. Earlier, I told you the perfect process has got a mean halfway between your upper and lower specification limit, which is your nominal mean. So the industry really need to know if the mean of your process is getting away from your nominal mean, and PCR wasn't capable of doing it. So the 10 years after PCR, the scientists and mathematicians suggested a new process capability index, which is PCRK or CPK. That is usually the sign that you see in the technical report of industry. And your PCRK is designed to take into account the mean of your process as well as the standard deviation of your process. So if we want to compare the value of PCR and PCRK, I can say that PCRK is your actual capability index. Because going back to previous page, you see it takes the minimum of your two one-sided PCR. So it takes the specification that is closest to the mean of the process. If you have the situation at your PCR and PCRK are equal, that means the mean of your process is equal to the midpoint, and that is your perfect situation. If your PCRK is less than PCR, that means your process is away from its nominal mean, and it's usually away in the direction of your specification limit, which is closest to your mean. Now, sometimes in industry, when you're producing something, you want to know the difference between your actual mean and your nominal mean. You can measure the difference between your actual mean and nominal mean by finding the absolute value of the difference between PCR and PCRK and multiply that by 3. I go to a graph that we have here. You see, in this graph, your upper and lower specification are very large. It's between 38 and 62. So if I find my nominal mean, which is 62 plus 38 divided by 2, it gives you the value of 50. In the first graph, you have got PCR equal to PCRK equal to as well, which is good. It says your process is very capable because its value is greater than 1.33. And from the graph, you can see where your products are, it is well between upper and lower specification limit. In the next graph, you are still capable, but you see the mean of your process is 53 now, which is moving away from your nominal mean. If I find that change is the difference between 2 minus 1.5, which is 0.5, multiplied by 3 sigma, that gives you 3. So you can see exactly, even if you didn't have the graph, you can see the mean of your process is away from your nominal mean by 3. And then you go further down, this is still a capable process. For away from your actual need a lot. And you can have PCRK, which is negative. But please remember, if you want to calculate the difference in your need, you have to take the absolute value. So don't ignore like this. You see, it's 2 minus 0.5 multiplied by 3, and you're away 15. So the formula helps you even if you don't have the graph of your distribution. You can still just use this formula and say, look, in this production line, the mean is away from the nominal mean by this method. Any question there?
Maybe you can continue, Mali.
Now, this table is very good. It allows make a decision based on your existing test. If you are using your PCR, it has to be greater than 1.3. But your one-sided identification limit would be 1.25. However, if you have a new process, you have to increase your limit. And I explained earlier why. For the new process, we try to make our sigma smaller, or you increase the length of your specification limit. So you have to have a larger PCR. For the safety reason, like the strength of the concrete that you are using to build a road, or the bullet that you are using for under a bridge, you need to have a larger PCR. Again, the reason is for safety measurement, usually you have a larger specification limits, so that will increase the value of your PCR. And if you have got a new process and your data refer to safety and strength, then it is even higher than the value. So this table is a good table to use to assess your capability. Also, if you don't have access to the statistical page, then you can just calculate your PCR and use this table to estimate the proportion outside every outside your specification. So you are either using PCR upper or PCR lower, and in the second column you are using your actual PCR. So if your PCR, for example, for 2 sides is 0.5, then you know that you will have 130,614 data falling outside your specification limit, and so on. So this is a good table to use if you don't have your limit graph and you still want to look at the number per PP is per million. Now, this page is important because sometimes I have seen a student put the specification limits and control limits on the same chart. You see, if you are using your specification limits, you only plot the individual data, because the specification limit look at the function of your product. Like if it is your laptop, it look at specification of your laptop and says, okay, the battery life have to be between 6 and 8. So for each computer, they measure the life of the laptop and the life of the battery, and they plot it against 6 and 8. We only use a specification limit to decide whether this or confirm the specification limit that market and customer have studied or not. But control limits only tell you whether there is a problem in your production line or not. Usually its value depends on the mean of your process and the standard deviation of your process. They are also a function of your sample size and risk of type 1 and type 2 error. So you should not use them together on this note. Never ever put them on the same graph. Either your graph is control chart that plot the mean range for a standard deviation or proportion of your defects in the sample, or you have got a specification limit in your individual measurements. Any question?
Ada pertanyaan?
Nothing, Bu.
Okay.
What?
Yes, Mali.
Okay. But the next example, that it says, it doesn't give you the raw data. It just tells you we have had a sample of size 4, the value of X limit for X bar and or S chart is given to you. And it says both X bar and S are in control. You are given the specification limit, and it's asking you to say whether this process is in control or not, and it is capable or not. Okay, to say whether it's capable or not, I need to calculate process capability index, comparing in 1.6. You see, I cannot use the statistical package because I don't have the raw data. For a specification limit are given, but for your process capability index, I need sigma. So I use the information given here to calculate my sigma. In Montgomery, if you are given the open control limit for S chart, central line for S chart, and lower control limit of the S chart, then you can use the following formula to calculate your sigma. Your sigma is S bar over AN. AN is an index given in a table in Montgomery. S bar is the center line of your S chart. So the center line of your S chart is always your S bar. So using those values, you get your estimated sigma as 1.085. And so your PCR is 0.76. And you can see that your PCR is less than 1.33, so I can say one process is not capable. Measurement error is something that I leave it ready to discuss it for you. What is an important part of quality control is measure the strength of the concrete. That measurement in an instrument itself has got some error. So in fact your reading that is your actual reading, is some actual value plus some epsilon, which is the error of the instrument that you are using. If you buy a camera or a drill or a tape, sometimes when you read at the back of it, it says the efficacy of this product is 0.05 or 0.002. That is your measurement error that you have here. That is your epsilon. So usually the instrument that you use give you the measure of your error. Now, if we do have an error in mode, this parameter is something that you have to carefully measure. It's 6 times the standard deviation of the error on your instrument. And so if I use that into my PCR formula estimate, in the denominator I don't have sigma anymore. I have sigma of my measurement including the error. So if I keep putting those values into my formula, the estimate of my PCR is obtained by this. You see, so it has got the value of C squared that we earlier measured. Now, this C squared is very important because it can give you that your PCR, when you have got measurement error, can never be greater than 1/C. So no matter how hard you try, if you have got measurement error and you calculate this, then you cannot have a certificate PCR which is greater than 1/C. So sometimes when you buy an equipment to measure your quality characteristics, you have to carefully read the error that measurement will have. Any question?
Maybe just go on, Mali. At the end, we can have questions.
That is one example that in there. You see, you have got your specification limits. That is a chemical process. And you know that you have got the measurement error of 6. So if I calculate C, my C is 0.6. And then for 1/C is 1.67. That means no matter how careful I am, I can never have a process capability index that is greater than 1.67. And then earlier I talked to you and I said, sometimes industry has no idea what is their capability index. If that is the case, as long as you know your data follow a normal distribution, you can use the confidence interval formula to estimate your process capability, to estimate your upper and lower specification limit. Both committee has got a table that is giving you a value of K based on what percentage of your data you want to fall within your specification limit, and what is your confidence interval. Example is here. I put one example. Let's say you have got 20 measurements. You know your data are following a normal distribution. You know it has got the mean of 350, a standard deviation of 10. But you don't have any idea on the actual specification limit. So to calculate your natural specification limit, one have a probability of 0.9 that 95% of your data fall within this specification limit. So your gamma from the table is 0.9, your confidence in your interval is 0.9. So if I go to the table for two-sided, my sample size is 10. I want the 90% confidence. So I read the value from this table, which is 2.5. And so your upper specification limit would be 370, and your lower specification limit would be 3 to 4. So that you can start with this value and then take action when you have got more data and more feedback from the market. Okay, that is end of my slide. Do you want me, Debbie, to take them to the mini tab, or you want to handle that?
Maybe I can handle that, Mali, or if you want to quickly show them how to create the PCA, the 6-pack, you can.
Okay, all right, I'll go then to the mini tab. Okay, everyone, to open your data, you need first open your mini tab. Mini tab data can be opened only on mini tab. Am I sharing the screen, Debbie?
Yes, Mali, we can see your screen.
Okay, everyone. The data that you have is on all viscosity. It is in economic textbook. And here I have got a sample of size 4, and all together I have about 16 samples. But the way that I have saved my data, which is the way that industry saves the data. So each row of your mini tab presents the raw data for one sample. I don't have the mean of this data, I don't have the standard deviation. So the first thing that I need to do is use a 6-pack to see whether these data are in control or not. So to use your data, your 6-pack, you go to a stat. Maybe can they all see?
Yes.
Okay. So you go to a stat and you click on quality tools. It asks you to do capability analysis. Capability analysis. So click on capability analysis. It tells you whether your data are normal or not. I want to go to capability analysis stat, and I'm assuming my data are normal. But if your data are not normal, you see you have got the option here. So in this case, I click on normal. It asks me how you have stored your data. I have stored my data on some sample models like that. And it asks me to write the codecs that contain your data. So my data is stored in codec C1, codec C4. I need to have my update and load specification limits here. So let's do my load specification limit as 10 my load specification limit at 50. And you see, if you do have your actual need for actual standard deviation, you can put it here. But it says it's option, so if you don't have it, it's okay. Then again, it is. Then you have some option, and I usually say click on your option because it allows you to enter title. And in the title, I say process capability. Or viscosity data. But I always like to say what is my sample size and whether I have the mean and the standard deviation after. So I want to add n is equal to 4, which is my sample size, mean and the standard deviation on. So when someone look at your graph, they know that this value is estimate. Okay. And then press OK. And you have got your 6-pack capability. You can see here your CP is 5.44. So your process is very much in control. You can see for your graph that your data are falling well between that. And also in the title of your graph, you can see your mean, your sample size, and you know that the mean and the standard deviation are provided by the data. Now I want to go to capability to see more data. Then I go to capability analysis. And again, I select. And then I'm going to 35 and 50. And you can put again your option. Then it's 4. Mean the standard deviation. Then almost you have 0 per million after your specification. Okay, any question?
Oke, everyone. Ada pertanyaan nggak? Ini sudah selesai tentang proses capability analisisnya. Jika ada pertanyaan, boleh disampaikan langsung ke Mali. Silahkan.
Ibu mau tanya.
Ya, silahkan. Sebutkan namanya.
Nama saya Winda Diemehta. Saya mau tanya, kalau datanya nggak berdistribusi normal itu kan ada 3 pilihan. Nah, yang salah satu pilihannya itu kan memperluas PCR-nya. Saya nggak paham Bu bagian itu.
Oke, saya kasihkan pertanyaannya ke Mali. Mali, there is a question about how to create process capability analysis if the process is not normally distributed. So
One thing that they can Johnson transformation on Minitab and make the data normal. But if they are doing that, it is very important that they do the transformation on the upper and lower specification limit aspect. So if your data are not normal and you wanted to adjust on transformation, say using Minitab, only at the end of my data, the value of upper specification limit and the value of your lower specification limit. So when it is transferring, it will transfer everything. And then when you have got your transport data that are now normal, you can use the transport value of your upper and lower specification limit. If they are using Minitab actually, they can choose the option of non-normal. And that would automatically transfer the data and transfer the upper and lower specification limit back. Otherwise, if they want to do it in other systems, you have to transfer the data. Also, therefore, they go to research papers. There are papers that tell them some of the PhD students of mine have used the capability analysis on it more sophisticated.
Oke, mungkin bisa sedikit saya jelaskan dari Mali tadi. Jika prosesnya atau data yang kita dapatkan mengenai suatu proses itu tidak berdistribusi normal, kita bisa lakukan transformasi box Johnson di Minitab, sehingga nanti spesifikasi limitnya juga bisa disesuaikan. Atau dengan secara simple, kita bisa gunakan tadi opsi non-normal, sehingga semua data berikut dengan spesifikasi limitnya itu disesuaikan untuk bisa ditransformasikan ke normal. Itu tadi saran dari Mali. Kemudian kalau mau metode yang lebih advance itu biasanya juga ada bagaimana cara mengatasi kenon-normalan suatu proses untuk bisa memberikan atau melakukan proses capability analisisnya. Begitu mungkin ya Winda. Kalau tidak ada yang ditanyakan, mungkin kita bisa cukupkan kuliah tamu hari ini. Mohon maaf atas ketidaktepatan waktu berakhirnya kuliah tamu ini, karena tadi kita ada sedikit technical problem. So Mali, I think they don't have more question at this stage. They will ask me later on maybe.
All right. Thank you everyone, and sorry for the technical problems. It wasn't my fault.
Thank you so much, Mali.
Thank you, Mali.
Bye. Maybe next time we can invite you again in another course.
Sure. Bye-bye.
Bye. Thank you. Terima kasih atas perhatiannya semua. Mohon maaf jika ada kekurangan dalam kuliah tamu hari ini. Sekali lagi saya mohon maaf dan terima kasih atas partisipasinya untuk para mahasiswa dan juga para dosen prodi matematika dan statistika. Dengan ini saya akhiri. Terima kasih. Assalamualaikum warahmatullahi wabarakatuh.